Section 6.7 is inverse relations and functions. I can find the inverse of a relation or function. Big ideas for this section. The inverse of a function may or may not be a function. When we square each side of an equation, the resulting equation may have more solutions than the original equation. And we talked about that a little bit when we were solving radical and rational exponents equations. We sometimes had those extraneous solutions, and that's what they're talking about there. If f and its inverse, this means its inverse, are functions, and if either maps a to b, then the other maps b to a. The range of a relation is the domain of the inverse, and the domain of the relation is the range of the inverse. If a relation pairs elements a in the domain to elements b of its range, the inverse pairs b with a. So what it's saying here is if we have a relation and we start with a as an input and output b, in its inverse relation, we're going to start with an input of b and output a. So it's kind of like your normal function goes this way and your inverse goes backwards. If AB is an ordered pair in the relation, BA is an ordered pair in its inverse. So x, y, and like our y value and our x value, they're the same values, they just swap places. So we would still read this ordered pair as an x and a y, but these values, whatever our numbers are, switch spots. When both the relation and its inverse are functions, they are inverse functions, and there's a diagram on page 405 that shows that. In example 1, we're finding the inverse of a relation. So the inverse of relation S here, these are like our A values here, and these are like our B values here. And for it to be an inverse, they swap places. So our B's go here and our A's go here. So every ordered pair flip-flops. X goes to Y, Y goes to X. So here, instead of having 0, -1, I have -1, 0. My X goes to Y, my Y goes to X's. So instead of having 3, 4, I have 4, 3. Instead of having 4, 3, I have 3, 4. So the graphs of S and its inverse here, we have S here, so I'm going to have 0, -1, 3, 4, and 4, 3. Its inverse, which we mark as S, little mark there, -1. I'm going to have -1, 0. I'm going to have 4, 3, and I'm going to have 3, 4. The graphs here are always going to be reflected over this line, y equals x. Okay, so here, 1 unit away, same. Here, same. It's like they just flipped over each other. We talked about reflections in x and y. Here, it's over this diagonal line, y equals x. It's where x and y values are the same. So here, if I start with 0, -1, I go the same distance, just in the opposite direction. So I go, instead of going down 1, I go left 1. Towards the negatives. Here, instead of going over 4 up 3, I go up 4 over 3, or vice versa. And that gives me my inverse. Here, pause here if you'd like and give it a try. We want the graphs of t and its inverse. So this is t, so I'm going to have 0, -5. I'm going to have 1, -4, 2, -3, and 3, -3. Inverse of t, my ordered pairs all swap. So instead of having 0, -5, I'm going to have -5, 0. Instead of having 1, -4, I'm going to have -4, 1. I'm going to have -3, 2, and -3, 3. So all my x's, 0, 1, 2, 3, are now my y's, 0, 1, 2, 3. My y's, -5, -4, -3, -3, -5, -4, -3, -3, become my x's. So I have -5, 0, -4, 1, -3, 2, and -3, 3. And again, if we were to draw in that line, and we had like wet paint on these pink ones and folded it over that, they would have landed on these white ones. So they were reflection over the line y equals x. In example 2 here, we want to find the inverse of the relation described by the equation y equals x squared minus 1. We can use the same idea here to find the equation. In our relations where we just had ordered pairs, we swapped our x's and our y's, and we're going to do the same thing here. The only difference is when we want to graph this and have it in standard type form, we want it set equal to y. So the first thing I'm going to do is swap my x's and y's. Everywhere I see a y, I'm going to put an x, and everywhere I see an x, I'm going to plug a y. Now, I'm still going to solve for y to get it in standard form. So I'm going to add 1. And then to get rid of the square, I'm going to take a square root. Okay, but remember, whenever I take the square root, I have to take plus or minus. So plus or minus x plus 1 equals y. And that is my inverse. On example 3, we are going to graph the two equations. So we have y equals x squared minus 1. And then we're going to have plus or minus the square root of x plus 1 equals y. So I'm going to do my original function first. X squared plus 1, we know it's x squared minus 1. We know it's a parabola with a shift down 1 because of the minus 1. So we go over 1, up 1, over 2, up 4 from our vertex in both directions. So we'll draw in this parabola. And with the first examples when we graphed, I didn't draw them in because all I had was points. But here, since I have those equations, I can connect them because any point would work if we made a table of values. Now, for my second one here, I actually have two parts. I have a positive and a negative. So when we graph these, okay, we're going to plug in some values. So I'm going to plug in like 0, kind of a table of values here. So when x equals 0, I get 0 plus 1 inside my square root, which is 1. Square root of 1 is 1. So I get plus or minus 1. I actually have 2 points here. So for x is 0, I have a point at 1 and negative 1. Okay. I'm going to plug in a negative 1 because that'll give me 0. So the square root of 0 is 0. And it's like, guys, we're just flipping those points. So we can either do this table of values and guess values, but now it's like, okay, so I need to get to the next perfect square, which is going to be 4, and I have to add 1 to it, so x is going to be 3. So rather than doing that, guys, we can take our points individually, okay, from our parabola. So right now I have a point at negative 2, 3. So I'm going to have a point at 3, negative 2. On my parabola, I had a point at negative 1, 0. So now I have one at 0, negative 1. I had a point at 0, negative 1. Now I have one at negative 1, 0. I had one at 1, 0. So now I have one at 0, 1. I had a point at 2, 3. So now I have one at 3, 2. Okay, again, we could have checked here and been like, okay, so 3 is what I add there. Square root of 3 plus 1 is the square root of 4, which is 2 plus or minus. So I have 3, 2, 3, negative 2. But that kind of takes a little bit more thinking, and that's fine if you want to do it that way. The other thing we can do, like I said, is we can take each of our points on our parabola and swap our coordinates x and y, and that will give us the points we need for our parabola. So again, you can either use a table of, or for our square root function, our inverse. You can either take a table of values, or we can flip-flop our x and y's. And this is what we get for our inverse. Here we're going to find our inverse. Feel free to pause and give it a try if you'd like. Again, to find our inverse, we swap our x's and our y's. So everywhere I see a y, I'm going to write an x. Everywhere I see an x, I'm going to write a y. And everything else about my equation stays the same. Now, we solve. Again, we want to solve for y. Divide by 2 to everything. And I get 1/2 x minus 4 equals y. Now, the graph of our functions here. I'm going to do my inverse first since I already have that color. I'm going to start at -4. My intercept. My slope is 1/2, so up 1 over 2. Up 1 over 2. Up 1 over 2. And then I'm going to connect those. Okay, now my original function, intercept is at 8. I'm going to go up 2 over 1. I can also go down 2, back 1. And connect those. And arrows. Okay, if we were to draw in our diagonal line here, we could see that they were reflected that way. We can also check a couple points. So here I have 0, -4, and -4, 0. I have I should anyway, have 8, 0, and 0, 8. I have 4, -2, and -2, 4. So my points are flopped, x and y's, which is what we want in inverse functions. So that's one way we can check and see if our inverses are correct. That's all I have for the first half of this section here.